Hello, this is part 3 of topic 4 on polymer viscoelasticity. In this section of the lecture, we're going to focus on modeling of viscoelasticity and being able to mathematically predict how a material will respond under viscoelastic conditions. It turns out that most materials can be modeled using simple spring and dashpot mechanisms. So for example, an elastic solid can be modeled by simply using a spring analogy and saying that the force on the spring is equal to the spring constant times the distance the spring is stretched. And this equation should look familiar to you since it looks very similar to Hooke's law, which says the stress is equal to the elastic modulus times the strain for a linear elastic material. Conversely, a viscous liquid is given by a dashpot type of model in which the force is equal to the dashpot constant B times the strain rate or the displacement rate of the dashpot. So here you have a rate dependence formulation. Viscoelastic materials are combinations of both a spring and a dashpot. A viscoelastic liquid, like a polymer melt, would use what's called the Maxwell model, or a series combination of springs and dashpots. Whereas a viscoelastic solid, which is what we're interested in, would be for polymers, and that includes a dashpot and a spring in series. So in this case, the force is equal to kx plus bx dot, or bx times the displacement rate. We take that equation, we can rewrite it as the force equals the spring constant times x plus b, the dampener ratio, times the change in x with respect to time. This includes both the elastic and the viscous component in the model. The Voigt equation can be converted to a stress-strain relationship by dividing by the appropriate dimensions. So the stress, which is the force divided by the original cross-sectional area, equals the elastic modulus times strain plus eta, the viscosity of the material, times the strain rate. Now to solve for Voigt's model for creep, we have to use ordinary differential equations. We're going to assume for creep that at time 0 the stress and strain are equal to 0, and at times greater than 0 the stress is equal to a constant stress sigma naught. So we can substitute in sigma naught, and dividing by eta gives us the following equation. Sigma naught over eta, the viscosity, equals the elastic modulus divided by the viscosity times strain plus the strain rate. If we solve this ordinary differential equation, we get an equation of the following form, where strain equals stress over the elastic modulus times the quantity 1 minus the exponent of negative ET over eta. The one term is the elastic term because it's sigma naught over E is Hooke's law, minus the viscous term, the exponent of negative ET over eta, the viscosity. If we plot this equation of strain versus time, we get the familiar viscoelastic response, which gradually approaches the asymptotic condition of the linear elastic material, or sigma naught over E, the elastic modulus. But the reality is that Voigt's model is not entirely accurate. Real materials have a more compounded influence, where we would have multiple Voigt models stacked on top of each other in series. So for example, you might have one Voigt model with a set of spring constants and dampening ratios, another Voigt model attached to that, and so on, out to T sub I, or tau sub I, with an applied force F naught. And that produces a curve as shown here for the multiple Voigt models. And you can see from this graph that the multiple Voigt model better predicts the behavior of polyethylene than the single Voigt model does. There's a number of factors that influence the rate dependency of creep response, and specifically that's the shear rate. As the shear rate increases, or the rate of strain increases, the stress-strain response of the material increases. It becomes more rigid and also stronger. And this is experienced in lots of materials, but most commonly in silly putty. If you allow silly putty to sit on a table with a hole underneath it, it will drip through that hole viscously, but if you pull on it rapidly, it breaks in a brittle manner.